All right, line W1, learning task 1, we're into our drives line. So we've gone through all of the three-phase theory, we've gone through some of the DC motor and generator theory, and now what we're doing is we're taking all of that, we're combining that with a lot of the electronics that we learned earlier this year, and we're going to go and create these electronic drives. Or actually, we're not going to create them, we're going to go and describe and understand them and understand how they're operating so that we can properly apply them and properly troubleshoot them. The very first one that we're going to take a look at is going to go and be a DC drive that we are going to go and have. And we've talked about the DC motor itself. We know that the DC motor is going to be composed of three main components. We're going to go and have the armature, which has been, this thing that we've seen represented as a circle with a couple brushes on the side. We are then going to go and have a series field. It's going to be identified with S1s and S2s. And then we are going to go and have a shunt field, which is going to go and be identified with my F1s and my F2s. And what we're going to do with all of these is we are going to go and combine them to go and get different characteristics. You should remember that a motor that has got predominantly series type of connections has got this incredible amount of torque that it's able to go and put out. The series field is obviously going to have to go and connect in line with the armature. So that's going to be a really, really torquey type of motor, but it's crap for speed regulation. Whereas my shunt is really, really good for speed regulation, but it's not so great with its torque amount. And so what we'll often do is we will combine two types of windings into the same motor, shunt and series together, which is going to go and give us what we refer to as our compound motor. And if we got a compound motor, that compound motor then has some characteristics, the torque from the series and the constant speed from the shunt itself. We've talked about connections of these. Now, the way that we connect these two together, F1 to F2, S1, S2, all those other things are going to go and change how the compounding is going to be. And we have got, this long shunt, short shunt, cumulative compound, and differential compound. And some of that gets really confusing to go and remember. Now, once we get a motor set up, it's going to be good to go. But when it comes time to reverse it, if I reverse either one of these two components, we know that we can set ourselves up for a world of hurt because we might change, instead of reversing the motor, we might just go to a differential compound motor or something like that. So rather than utilizing those to go and reverse, what we are going to see is that we're going to go and reverse our armature. So inside of our DC drives, we're going to do the same thing. We're going to use the DC drives to go and control the armature. And when we go and control the armature in these DC drives, we're going to be able to go and reverse as well. The other thing you should remember about armature control is that the amount of speed that I'm going to go and have out of this thing, the amount of speed and the amount of torque that I'm going to go and have is all going to be based upon my armature current. If I were to go and have full armature current, I'm going to go and have full speed. If I reduce my armature current, I'm going to go and have reduced speed. And we also know that if I want to make my motor go faster, I can go and overspeed it by increasing the amount of resistance inside of the shunt field, which is actually increasing the amount of resistance is decreasing the current inside of the shunt field. Some of our DC drives will give us that option. Most of them are just going to go and deal off of the armature itself. The motor that we are going to go and use with these is going to be a compound motor, predominantly shunt field, which means that it's going to be better for constant speed regulation, and a light series field winding. In other words, it's just got a small amount of series field winding to keep that torque up. And they are going to be specifically designed to operate on the waveform that's going to come out of these. Now, we're going to have a chopped up waveform, which means that we are going to go and have, instead of us having a nice, let's just take a look at a rectified DC waveform over here. If we are going to trigger this waveform, which we're going to do with SCRs, we know that we're going to be waiting. We're going to have a firing angle, and then boom, we're going to go into this conduction angle. This over here is an extremely rapid rise in voltage. If you imagine, standing next to your buddy, if your buddy sticks his hand up against you, we can't have contact, it's COVID, but whatever. But if your buddy puts his hand up against you and pushes, fairly slowly, you're just going to kind of rock back a little bit and you'll be like, dude, what's up? But if your buddy does a really rapid hand movement, we call this thing a punch, there's a lot more impact that you feel off of it. We get the same type of thing on rapidly rising edges. These are like punches to my motor windings themselves, because we're going to go and get rapid rise in the amount of current. We're going to get a rapid rise in the amount of magnetic stresses inside of there. And as a result, all those little windings, which are wound super, super tight around these cores, right? They're going to be ferromagnetic cores. they're going to go and move up against there, and so there's little bits of chafing and the insulation can start to break down, etc. So what we have is we have to have a special type of inverter duty that we are going to have, or drive duty that we will have on these DC motors. Do not use a regular DC motor on a DC drive because it will fail. You'll have no explanation for it other than that, I don't know, it's not rated for it, and that's exactly what the explanation is. It just wore out because usually it's just going to be windings that are going to be shot. Let's talk about the DC drive itself now. The DC drive itself is broken down to a single line diagram over here that they're showing us. This single line diagram contains a bunch of different components that are going to be inside of my DC drive. Now, the DC drive composes everything inside of this box over here, with the exception of the actual, fields and armature. Those are going to be connections that I'm going to go and have on the outside, but everything else inside of that box is going to be inside of my DC drive. What I'm going to do is I'm going to go and feed power in. It can be three-phase, it can be single-phase. It really would not matter which one we would have. We're working with a three-phase one, which means that we're going to have 6 SCRs that we're going to have on our bridge. But if it was a single-phase one, we would just have 4 SCRs on the bridge, and the rest of the controls would be the same that we would see inside of here. We see that once we bring power, input power into the drive, we're going to have a disconnect ahead of that drive so we can isolate it, work on it. Remember, we cannot use semiconductors for isolations, but we'll be able to move into that drive. Once we are inside of that drive, our power is going to be distributed across 2 sections. One of these sections is going to be my field section. The field section is going to go and have protection, that's that fuse. Then it's going to go and have rectification. It's just going to go and take that AC and it's going to go and convert that into DC so that we can go and apply that to my field. Excuse me. In some cases, what we will also have is we will go and have control. Right here, they're just showing this as a regular diode bridge. If my DC drive, it gives me the option of going into above base speed, then I would also have control inside of here, which would mean that we would be looking at another rectifier set that we would have inside of here, and that rectifier set would tie back to a bunch more controls. They're not showing us that one on this one, they're just giving us a constant field on this one. The field connection is just going to be 2 terminals inside of the drive. Literally, they're just going to be labeled F1 and F2. And we just take our motor connections from the motor. We run 2 wires back from the motor conductor, and we just terminate them underneath those 2. And that's all we need to do for it. The other section that we are going to go and have is going to now be taking in, once again, our AC. Our AC is going to be measured. We're going to do that through a current transformer so that we can go and calculate the amount of power, right? We'll be able to measure the voltage. We'll be able to measure the current. We can therefore calculate the amount of power that we have going through here. We then go and run that through a SCR bridge, and the SCR bridge is going to chop that up and feed that out as DC. We're going to take a look at the operation of that later on. That bridge is then going to get fed out as DC. At that point, why don't I change arrows over here? We'll go to a red arrow now that we're into the DC. It's going to get fed out as DC, and that DC is going to go and feed out to my armature. My armature contacts are going to go and have A1, A2. If I have got a motor that has got the series wired already in with the armature, then I just connect the A1, A2. Some cases, you're also going to go and have a series field. If you have got a series field, what we'll often see inside of these drives is that you're going to go and have 4 terminals that are going to go and look like this. Hold on a second. And they're going to be labeled. We'll just draw the board in the background there. So that's the circuit board there. They're going to go and label A1, A2, S1, S2. That they're going to have, and really what's happening inside of this board is that they are going to go and feed out from my A1 or from my S1 to my S2 unless it's already been pre-done. If this thing has been pre-done, so out in the field, here's the armature and the series field together, all that I would need to do is feed that in there if I can't separate them inside of the motor. If, however, I can separate them inside of the motor, then I'm going to go and feed the series field into here. And what they'll have inside of here is they're going to go and have a jumper. That's usually going to be jumper in S1 and S2 because the S1 and S2 goes through into this A1, A2. That is going to be over here. And there's going to be some other switching that will happen inside as far as, rotation that I can control, etc. If I've got something where I've got a broken apart winding, what I'll do is I'll take my armature directly into here, and then I'm going to go and remove that jumper, and instead of that jumper, I put in my Series 1, Series 2, like that. Still the same, if you take a look at the current path, it's still going to be through the same components inside of these. Manufacturer's documentation, once again, is going to tell you the best things to be doing, so don't just throw that thing out right away. Okay, so we've got our DC that we've got coming out of the drive over here. Then the rest of this is all going to go and be based off of what I have for a desired value of speed. If you take a look at this, you see that we've got voltage. You see that we got this little triangle over here, sometimes used inside of electronic circuits. It's another representation of a type of ground or a common or a chassis that we're going to go and have. We see that we've got a potentiometer. That's a resistance placed across here, and we're going to be measuring a value of voltage. We're then feeding that into here. Look at that little triangle in there. Do you know what that is? That's an op amp over there. We're going to be measuring that value of voltage coming off that rheostat. We're going to measure that, and then we are going to go and put that into this circuit over here, which is the XL D cell. This is all on the board, so you don't need to worry too much about it. That XL D cell is going to go and say, hey, this is where the reference is. This is what I need to go and have. So I'm going to go and output a certain value into here. This is a symbol for a comparator. That comparator is going to go and compare feedback from the motor. This is what I want. This is what I have right now off of that motor. And the way that I know what I have off the motor is one of two things. There's going to be jumpers. I can either select that I'm going to go and run it off of a tachometer that's going to go and measure. It's a physical speed sensor that is going to go and generate a voltage. EG is equal to BLV. That's going to go and generate a value of voltage based upon the speed that that motor is operating at. So that's one way that I can get that signal back into what I actually have. The other one that I can go and get that signal back into what I have is for me to go and take a look at what my output is. And this is more of a guess. It's not as accurate that I'm going to go and have, but it's going to go and say, hey, what are we feeding out of the drive right now? And how does that compare to what I'm desiring to go and have? So it's less accurate, but it's going to be plenty accurate for most applications that we're going to have. All of that together compares into here. So what I want versus what I have. I'm going to go and tell you what. I'll make it easier on myself. Anything that I want, I'm just going to have a bubble. It's like a thought bubble, a dream bubble. Anything that I have, we're going to go and just put a square. So over here, we've got what we have. Over here, we have got what we want. What we want, what we have together is going to go and generate what we refer to as an error signal. An error signal does not mean that it's bad. It just means that it is off the mark, off of what we want. So if it's too high, what we have compared to what we want, then it's going to go and adjust it down. If it's too low, what we have compared to what we want, it's going to go and adjust it up. And so this is going to go and create what's called our major speed loop regulator. So once again, we're going to feed that into there, and then this is going to go and adjust my amount of current that I'm going to go and have. I'm going to have, this is going to say, this is how much current I should have in order to achieve what I want versus what I have. So it's going to go and say, I should have that. Then that's where the CT comes back in, and the CT is going to go and tell us what we actually have. So now we are changing over this over here is what we want to have, and this is what we actually have. So it's, once again, it's a comparator that is going to go and generate what we refer to as error. Once again, that error, the difference between the current that we're feeding through versus the current that we should be feeding through, is then going to go into my minor current loop regulator. This is kind of a bulk adjustment that we're going to have. This is going to be the fine tuning of that, and that fine tuning is then going to go and create a signal that we're going to go and send to our trigger unit. Our trigger unit over here is just going to send the pulses to the SCRs at the correct time in order to put out the correct value of voltage with the correct amount of current draw that's going to go and run our motor off of it. It's a really complicated looking thing. I mean, this is the simplified version, right? We're just a block diagram. We don't even have a single transistor, drawn inside of here. We're not looking at voltage drop or anything like that. But all it is we are seeing comparisons of stuff that we want versus stuff that we actually have inside of here. And that's just going to go and be fed all the way through, and the motor is going to be run off of that. It's what we call a continuous feedback loop, or closed loop control over here, where I have an output that is feeding back into my inputs and readjusting itself. So it's continuously saying, hey, what am I doing? Is this what I should be doing? Yes, okay, I'll keep doing it, or no, then I'll adjust, to become what I should be. inside of here. Okay, let me see, what else did I want to talk about? Oh yeah, dynamic braking. You guys love braking. Dynamic braking is where we are going to go and change a motor into a generator in order to go and slow it down. They don't show dynamic braking inside of here, but a lot of my drives do give me the option to go and apply dynamic braking. And all that the dynamic braking is going to do is it is going to go and cut in right in over here. It is going to go and cut in, I'll draw it as a single line as well, resistance. And that resistance is really only going to go and cut in, we'll stick a contact off of it. That resistance is only going to cut in when I actually want to go and slow down that motor. In some cases, they will go and have control on this, where they'll actually run the control so we can adjust the amount of braking. They'll go and run that through FETs. And then the FETs are going to just adjust the amount of current that I'm going to be taking out, so I can, choose to have a really fast braking or really slow braking or anything in between, the coasting down speed to a really, really rapid stop that I'm going to go and have. There are additional levels of control that I can have inside some of these drives based upon, how much I want to spend on the actual drive and what I'm looking for it. A lot of my drives are going to provide me with the option to go into either forward or reverse. By going into forward and reverse, all it's going to do is it's going to interchange the positive negative that's going to be coming out of the SCR bridge. Once again, it's going to be done electronically. But we would be able to go and reverse that, and because we would only be feeding that to the armature, remember that inside of there we've got terminals that are going to be for my S1, my S2, my F1, and my F2, right? We got A's, S's, and F's, as well as we often have got B's or DB's, which are going to be my braking ones that I'm going to have. That's really all I'm doing, is I'm connecting onto terminals that are going to be sitting along the bottom of a board over there. So my armature, because my armature is going to be connected in over here, I'm going to be able to take that armature and reverse. This is really why we like to have that armature and the series separated. We did that illustration earlier showing where we had that jumper in there. The problem with using a motor where I have got the armature and the series field together is that then when I go and reverse the motor, I'm not only reversing, I'm also changing the compounding, and that can be really bad in some of my situations. That's why we prefer to put the series field in on its own set of windings. So we're going to be able to go and reverse. We're going to be able to go and brake. Once again, the braking is just going to be where I'm going to apply connection through my board like that to my external braking resistors that I'm going to have outside of there. I'm able to go and provide non-reversing with regenerative braking. Regenerative braking is where I'm going to go and take what I have, instead of using the braking resistors over here and taking that heat off, or taking that power off as heat, I'm actually going to go and feed it back into the DC system itself. That would be regenerative. And then I'm also able to go and have that regenerative reversing with 4-quadrant operation. 4-quadrant operation is where I can run in forward and I can run in reverse. You should remember this stuff from earlier on where we talked about quadrants, where we have got, forward motoring. We're going to go and have reverse. These are going to be my motoring. And then depending where volts and currents are, I'm going to go and have regen and regen. One of them is going to be a forward regen, one of them is going to be a reverse regen, and it all, once again, which is in which quadrant, really depends upon whether I've got volts and currents or whether I've got currents and volts on opposite axes. But it's where I am going to be running back, creating regenerative braking. I'm going to be forcing my current through in opposition to the voltage, which would mean that it would be changing from a load into a source. Operator controls are really, really simple on these. We have the most complex end. We have to go and connect everything into the little terminals, which isn't that bad. And then we make it simple for our operators. The operators themselves are usually going to go and have a little small toggle switch on the front cover. The toggle switch does not disconnect power that comes into here. The toggle switch just, shuts down the control circuit. It's going to be closing this off so that we don't go and fire anything out of here. There'll be a little on-off. Sometimes there'll be a little, forward-reverse, one of those little toggle switches that you can kick it into either direction. And then there's going to be a potentiometer on the front as well, so they can go and adjust what the speed will be. Sizes and ratings of these common values that we are going to have are going to be based upon what the input is, because we know that whatever I put into a DC drive is going to be my AC, because that's what we transmit all the way around the province with. And then I'm going to have to knock it down to DC, which means that we are going to be moving smaller in a lot of our cases. Small DC drives up to about 3 horse are going to be fed off of single phase often. They can be fed off of 3 phase, but they're usually going to be spaced for the single phase. They're going to go and have a 90 volt armature voltage. Let me just draw that out over here. 90 volts DC is what that armature is going to be operating up to. It's just a rectified and filtered, in a lot of cases, value of DC that we're going to go and have out. 90 volts DC, by the way, hurts. It hurts so bad, so bad. I can't even tell you how bad 90 volts DC hurts. I've never taken 180 volts DC. I don't know, I'd probably die or something like that. I've taken 120. I've had line-to-line 240 once, which was unfortunate. I've even had 347 twice. Where I've taken 347 volt shocks. It doesn't kill you every time. I got lucky twice. But 347 hurts a lot, but it does not hurt nearly the same as 90 volts DC, because anytime that you are working with a good quality drive is going to have filtering, which means that it's going to keep that voltage level high at that 90 volts. If I'm taking 120 volts, yeah, it's peaking really high, but it's dropping as well, and it's reversing in the opposite direction. Whereas this 90 volts, that sets up current flow through your flesh, and it is continuous current flow. Yeah, just be very careful around these DC drives. I know we work around 120 all the time. Some guys out there, really don't feel it at all. They say, oh, I can touch it, it's fine, it doesn't hurt that bad. 90 volts will hurt a hell of a lot worse. So my armature is going to be operating at that 90 volts over there. I've only touched it once. I was very, very careful after that. My field is going to be operating at a reduced value of voltage that's going to be around 50 volts. And these are standard ratings of these motors. If I've got 240 volts, I'm able to go higher because I can go and rectify line to line, which means that my armature is going to be double and my field is going to be double as well. We're looking at 180 volts, versus 100 volts that we are going to go and have. Anything that is going to be above that 3 horsepower limit for sure is going to be dealing with 3-phase. And when I go into 3-phase, they give us a pile of different values of voltage once again. 240 volts, 3-phase, that's going to be off of a delta system rectification. I'm going to be able to get up to 240 volts DC coming off the armature with a field, the shunt field, that's going to be at 150. 480, I'm going to go up to 500 DC. And 600, I'm going to go up to 700 DC. You'll note that those voltages are higher because you got to remember that it is always a 0.707 that we're looking at, right? You go to a peak that's going to be higher. 480 volts is my RMS value. My peak is actually going to be way higher off of that. It's sitting about 680 for the peak off of a 480, which means that 680 easily we can rectify down to that 500. As far as mounting and wiring of these things, same thing as always, follow your Canadian electrical code. Make sure you're doing things properly and refer to the drawings, particularly the drawings that deal with your spacing that you are going to go and have, because these things are full of semiconductors that are going to, in a lot of cases, be attached to the back. The backs of these are often finned vertically, which means that they need to be mounted in that vertical direction so that air can go and travel through there, strip away the heat, carry that away. Once again, make sure that this thing doesn't sit too tight to the top of any sort of like drip shield or cabinet or anything like that you might have, because that's going to stop that airflow from happening. Don't want that. We want to make sure that we've got that airflow. The DC motor itself needs to be set up. Physically, it's going to be aligned usually by my millwrights, because they're the ones that have got the tools and the know-how. They're better at it than you and I. That's just what it is. And I do have to go and watch these things for deratings, because if this thing is going to be operating at high altitudes where I don't have a same amount of oxygen, and where it's oftentimes going to be, drier as well, then I'm going to have to, just be really careful with them, because you start to go and lose that ability to build the patina on the rotor. You need to go and have that. That's why they talk about this, above 2,000 meters, that you're going to have to derate it. And if I have got surrounding air that is too dry, once again, I cannot build that patina as well. The other issue with going up to high elevations with DC, whether that's going to be DC mounted inside of a structure on top of a mountain, or whether that's going to be DC that's going to be inside of an airplane or anything like that, is that as we get higher, the atmosphere gets thinner, which acts like a vacuum, and so the windings, which would have been wound somewhere down near sea level, are going to have more pressure, and there's going to be more pressure inside. You got to think about the windings themselves as having billions and billions of tiny little bubbles of VOCs, volatile organic compounds. Those are going to push out through the windings because everything around it is going to be a vacuum. So they tends to break the windings down as well. As far as my wiring is pretty straightforward. Make sure it's going to be rated for the current. Make sure it's going to be rated for the voltage that we're going to go and have. And then anything that's going to be a control, which is very common where we're going to go and have, the DC drive that is going to be coupled fairly close to the DC motor. We don't want to go a long distance with DC because DC has massive amounts of drop. So what we'll do is we will feed AC, we'll mount the DC drive fairly close to that motor, as close as we can based on the environment. But in times we're going to have to go and have our operator station that's going to be somewhere out here. This stuff that's on the front plate, any of these switches or rheostats and things like that are going to go and have associated terminals that you're going to be able to go and extend them somewhere further out. If you do that, make sure you are using a shielded cable. This is one of those ones that has got that aluminum biler type of thing that goes around the conductors. It's there to take off unwanted signal because we're working with small amounts of signal, particularly on our analog signals, the voltage reference that we'll go and have. And so any sort of induction would go and cause this motor to be getting triggered. It's going to get triggered to go a little faster, a little slower, just based on surrounding induction. Make sure those shields are only tied together down here. A shield, by the way, is not a ground. You have to be very, very careful about that. We'll talk about this in AC VFDs as well. But a shield is not a ground or a bond or anything like that. It is a screen. You still have, inside of this cable, you should still have a bond. That bond is going to get attached here. That bond is going to get bonded into this box over here. But the shield itself is going to be an open loop, basically. So it's basically a tube, a sock that goes over top of this entire thing. We take it back to the source, and then we ground that shield only at the source. It's not there to go and ground devices. It's not there to ground the cable. The bond that's inside of the cable does that. It is there just to go and pick up anything unwanted and then drain it all the way back over here so it does not induce anything onto these. Okay, that is it for the first part over here, describing them. Let's talk about the operation of the power conversion inside of them now.